much. All right, so jet finding in Julia. So this is work that I've done together with Philippe Gras and Attell, who've been helping with this. And I want to tell you about, I suppose this talk actually, it's a little bit about the algorithm that we've implemented, but it's also a little bit of a sort of journey of discovery of Julia, of how we started just investigating things and, looking at various aspects of performance and ergonomics, and came to some very positive conclusions about Julia as a result of that. So I didn't know how much people would know about high energy physics, so I thought it was probably worth a little reminder of what it is that we're doing, particularly the experimental program at CERN. So CERN is located on the French-Swiss border, close to Geneva, and our flagship accelerator is called the Large Hadron Collider. So you essentially start with a gas bottle full of protons, and then you spin these up through the accelerator complex, and they get faster and faster, and eventually they go into this ring here, which is the Large Hadron Collider, where they will collide at the four principal experiment sites. And they reach 14 TeV, the two proton beams, which is the highest energy that you can reach, at least in a human particle accelerator. Nature still does a bit better in some circumstances. At each of the experiments, you have a big detector. So the idea here is that you're wanting to crash these protons together, and this will allow you to probe and explore some of the very most fundamental forces in the nature of the universe. Our experimental program, of course, is very much based around Higgs physics, which was discovered over a decade ago, but we still don't understand all of the properties of the Higgs boson. And there are lots of very active experimental programs to probe dark matter and the matter-antimatter asymmetry. And then, of course, one is always on the lookout for something that you didn't expect at all. So, what is the real unknown? So the LHC is providing 30 million collisions a second to the different experiments, and there's a very sophisticated trigger system which is going to select a small fraction of these for offline analysis, because we can't afford to store them all is one thing, and actually the vast majority of the collisions are physics that we already understand quite well, so it would be useless, in fact, to store all of these events. Okay, so talking about events, what do these actually look like? So this is an event display from the Atlas experiment. The interesting bits of the collision, so the very high energy interactions that you get between the quarks and the gluons inside of the proton, in general, these decay almost instantly. Okay, so you never have a chance to actually see a Higgs boson itself. You're only going to see what it breaks up into pretty much instantaneously. So this is a view of an event display from Atlas. So you can kind of see in the middle here is actually where the beam collided. It then changed, it produced a Higgs boson, which decayed into two B mesons and some W boson, which then decayed into a muon and a neutrino as well. So because all we see is the mess, I mean, it always reminds me of my kids when they smash something up and you go into the room and you think, oh my God, what was that originally? And that's kind of what it's like. So you see the decay products, and from that you have to reassemble what was actually going on inside of the detector. Now, the bit which is interesting for this talk here are these things which are called jets, which are indicated by these cones. These cones are going to come back later on in the talk, and they've been reconstructed there, which is essentially a spray of high energy particles, and you want to try and understand what was the source of those particular particles. So jets, if you take a two-dimensional view of a jet, they look a little bit like this. So you have some original high-energy unstable particle that decays into different pieces. These pieces are the things that you actually detect inside of the detector. They interact with the detector material to produce more and more energy deposits and particles, so you get more and more children. of the parent particles. These get captured in the piece of the detector that's called the calorimeter, and the goal is really to take all of these pieces and reconstruct what the parent particle properties actually were. So this is what jet reconstruction actually is. Okay, so how do we do this today, and how might we do it tomorrow? So in high energy physics, our experiment software is based on C++ and Python. Each of the four big LHC experiments has about 6 million lines of code. As Perry already mentioned, it's probably in total 50 million lines of code that are used across the entire field. Perry told us quite a lot about the wrappers that he's done to the main simulation package, Xeon 4. And later today, Jerry will talk about reading the specific data formats that we use in high energy physics with en route. That's at 5 o'clock if you want to catch that one. So like I say, yeah, mostly C++ and Python today, but we want to be open to new opportunities like Julia. And it does happen, of course, when you think about it. Our field 25 years ago, everything was written in Fortran. Now almost nothing is left in Fortran, so change definitely does happen. And we wanted to try and evaluate different languages. This is a multi-dimensional thing because one is looking as well as the algorithmic performance, also about the language ergonomics for different implementations. So we were looking for something that we could try out Julia with. And we decided that jet finding was a good test case. It's a good algorithm to do because we didn't want it to be so simple that it doesn't add very much information beyond general metrics that one might have and micro benchmarks of Julia, where we know it performs rather well. But we also didn't want it to be so complicated that it would take absolutely ages to do the Julia implementation. So jet finding is a good example of why I would call this a Goldilocks algorithm. As I already explained, the goal here is to cluster calorimetry energy deposits into jets, okay? And you can see an example of what the output of that looks like there. Here what is shown is actually each of the original energy deposits, and there they are colored according to the way that they have been aggregated into jets. So each of the colors represents a different jet that we've managed to reconstruct. Now, there's actually a very optimized C++ package, which is used ubiquitously inside of the field, which is called FastJet. It implements a number of different algorithms for jet clustering. At the LHC, certainly for primary narrow jets, anti-KT clustering is popularly used because it has these two properties of being infrared and collinear safe, which I'll explain a little bit more about in a moment. But let's just sort of run over the algorithm. What does it actually do? So you start the algorithm, you define essentially the size of the cone into which you wish to reconstruct jets. So 0.4, like I say, is typical, although there are some large radius jet studies that might use cones of 1 or 1.5. And then you have this bunch of particles. So you're then deciding, okay, I've got all this mess of particles here. How am I going to combine them into jets and build up the jets? So in this case, what you do is you measure the geometric distance between all the different pairs of jets, as long as it's less than r. So you're basically saying I will never join together two things which are further away than r. So you look at the geometric distance and you work out the closest neighbor for each of the clusters, but then you define a metric distance. So you don't just use the geometric distance to decide how you're going to do the recombination. You use a metric distance, which is also based on the transverse momentum of the particles. And if you use -1, you get anti-KT is the algorithm. What distinguishes that is essentially that you will favor merging to jets that have a high PT already, okay? If you use 0, then you're using purely the geometric distance, which is the Cambridge-Aachen algorithm. And if you use +1, you're essentially favoring merging very small energy clusters at the beginning, which is the inclusive KT. Okay, so you work out that metric distance, you then pick the jet which has the lowest value of that Dij metric, and then you merge those two. And you just basically continue that until there's no more mergers that you can do. And it's a nice algorithm to try because this part here that you have of measuring for each of the particles can be parallelized. But at the end, you have this kind of serial step where you need to optimize to find the lowest Dij. Okay. When you actually do that, this is what it looks like. I've built this little animation so you can see, but I think you very much get the idea here that the things are being clustered into places where you already have a high amount of energy. So this is the actual reconstruction process as it proceeds. It's because you're reconstructing into high PT jets, it means that if you add an infinitesimal amount of energy to the event, it will only be added right at the very end. So it can only produce an infinitesimal perturbation to the final result, which is called infrared safe. It's also called collinear safe because if you take an energy deposition and you just split it into two, then those two pieces will tend to recombine immediately, and so you don't perturb as well the final result. So this is what you're aiming for. This is a very nice property of anti-KT jet reconstruction, which is why it's so popular. Okay, there are different strategies for doing this, and we looked at two different strategies for implementing the algorithm. The one is called N2 plane, which is just a basic strategy where you consider all of the active clusters at any particular point in time. So you just have a global pool and you're considering everything against everything. And then there's an optimized version for higher densities, which is called the tiled implementation. And here, the trick is because I will never merge anything that are more than the distance r apart, I essentially divide my space into tiles of r size. And then if I'm at this point here, I'm considering a jet in the center of this circle, I only care about these 9 tiles, right? Because I can't possibly merge anything which is outside of that. So the tiled algorithm, of course, it involves quite a lot more bookkeeping. You've got to build up the tiles. You've got to work out which clusters are in each tile. But the idea then is to reduce the amount of work that you actually need to do. So it does, the basic algorithm does more calculations, but it's slightly more amenable to parallelization as well. So those are the two different strategies that we wanted to implement. Now, we actually looked at a number of implementations, and I'll give them here. So of course, our benchmark is this FastJet package, which I already mentioned, which is a very optimized C++ implementation. That was also kind of our reference in terms of the results. So if we get the same as FastJet does, then we know we did a good job. We thought, well, you know, Python is super popular, so why don't we at least just do a test of what things look like in Python? And we did one in pure Python. Of course, we didn't expect it to be fast, but we thought, you know, ergonomically, it's a good test to do to check that it looks quite good. And then a lot of my Python colleagues always say to me, yeah, but you know, of course, Python's slow, but you know, you use Numba, you use NumPy, you use all of these things, you can accelerate it, it will get just as fast. Okay, all right, I'm going to give it a go. I'm going to use Numba and NumPy and see if I can get things to work. So we as well as the Julia implementation as well, and we presented the results about a year ago, and these were the results that we got. So at that particular point in time, I think what's noticeable is that in Julia we got close to the performance of FastJet, but we didn't quite make it. We were still some 12% off. In the tiled algorithm. In the plane algorithm, Julia was a lot faster than FastJet, and the Python implementations disappointed. The pure Python, as expected, was really slow, although it was nice to work with. The accelerated Python, it was just really hard. You just could not cast the problem into the way that Numba and NumPy actually wanted it to be. So we were happy with the tiled result, of course, we got close. We were delighted with the plain result. We were very excited about that. But it's recently turned out that actually FastJet's behavior at this working point is quite pathologically bad. So despite the fact that everyone is using it, it has really poor performance at this particular working point. If you widen the cone, it gets quite a lot faster, and then the advantage of the Julia implementation is quite a bit less. But what was the ergonomics experience like? So, you know, the performance was kind of as we expected. Certainly we got there with Julia and got to good performance, but what was it like to actually work with? Well, like a lot of high performance C++ code, FastJet is really C that masquerades as C++. It uses the kind of traditional layouts and structures that you would use in C. It's actually pretty well written code. You know, I've done quite a lot of C in my life. But of course, it introduces some difficult points as well. So you have pointers to pointers. It can be quite difficult to reason about the code in different places. It's quite difficult to work with user types in FastJet. So you tend to have to do EDM transitions yourself, or you need to use templating to compile against your particular user types. I mean, I think the ecosystem for C++, everybody knows it, so it's very old school, not so easy to use at all. For Python, the pure Python code is rather easy to use and reason about, so it was nice to work with, but it's horrendously slow. The Numba and NumPy accelerated code became very unwieldy as the problem needs to be cast into NumPy array layout, which is not so obvious for this. I was quite surprised. This was the first time I tried to use Numba. And Numba acceleration doesn't work for some very simple things like array index wrangling is not supported, so you have to rewrite the translation between linear indexes and Cartesian indexes, which was kind of surprising. All of the way in which the algorithm works, there is some Python level logic even in the accelerated version, and that's why it ends up being slow, because it ends up being kind of killed off by having a loop inside of the Python layer. Julia, well, it was great actually overall, I would say. There were a few things that kind of stand out as, oh yeah, I love this as a sort of first experience with the Julia language. The broadcast syntax is really great. This is the way that we make some compact arrays that we are going to use for doing calculations and distance measurements, but that was really easy to use. I think the optimization macros are so easy to apply. You know, it's not like switching on -03 in your C++ code. You can really go to the piece of code where it matters, and you can say, okay, I need to optimize this particular bit of code, so it was great. And a really super ecosystem for developing and supporting packages. So the debugger was excellent. You know, the fact that you have the plotting infrastructure there in the language, which is still fast, was really good. Profiling, basic physics types, it was great. It is fast, but of course I would say that the algorithm is still critical. I mean, it doesn't do magic, right? You still have to write a good algorithm and then let Julia take over from there. I wanted to point out some less good aspects. Probably these are to some extent due to my naivety when I started this, but there were a few places where I sort of was banging my head and discovered some, like, oh, I didn't expect that at all. So I was doing some code debugging and I left a debug macro in a hot loop, and God, that costs a lot actually, even when you're not in debug level. So don't do that, I think, is the lesson that I learned. And then there was one weird place where I slightly refactored a piece of code, and in a branch which is not really taken, actually, because it was just a check to avoid dividing by 0, I mistyped the name of a variable. So it was an undefined variable, and that killed the performance. I didn't get an error, but it killed the performance. So that was kind of like, oh shit, I really didn't expect that at all. Probably there are some static checkers that I could have used to catch that one, but I didn't know about them at the time. I have to say that ultimate optimization seems to be quite hard because of the way in which the entire algorithm works. It's not just like a spot. I'm using I want to look at the LLVM code for just this piece of code. I'm trying to profile the entire algorithm. You get into Julia internals quite quickly. And I noticed that the JIT output can be sensitive to what I thought were quite minor code changes. And then I looked at my flame graph and I was like, oh, shit, this is completely different. I don't know what the hell this happened here. So yeah, I'm sure that you could work on that. Certainly we got it to a place where the performance was though very good. Some improvements, actually, after we initially presented the results, I realized that there was a very significant time in that serial step, finding the minimum Dij. And of course, that's actually, although that's kind of serial, it's actually kind of amenable to parallelization as well, because you can use a divide and conquer approach. So I used the loop vectorization macro, and that sped things up enormously, surprisingly enormously, actually. It's about almost 4 times as fast to use that piece of code, which is there, over the normal built-in Julia findmin. So yeah, I really hope loop vectorization stays. Please don't get rid of it. It's going to make me very sad if it goes away. So this needs to still be there. Okay, where are we for the performance right now? So for the Julia jet finding, this is sort of pretty much what we would expect, that you can see that the tiled algorithm scales a lot better with the average cluster density. The plane algorithm doesn't scale so well, so you would tend to only use the plane algorithm at this very low density regime, where it is a bit faster than the tiled algorithm because it has these lower overheads. If you compare to FastJet for the plane algorithm, as I already said, it's quite a surprise that FastJet has this quite pathological behavior for these small cone sizes with the plane algorithm. But even if you go to a wider cone where FastJet behaves a lot better, Julia is actually faster by about 20%. In the low density regime. At the higher density, you'd be using the tiled algorithm anyway. And then for the tiled algorithm, we're about 15% faster than FastJet for this tiled strategy due to the more optimal search for the minimum value of the distance metric. It would be nice to understand maybe in a little bit more detail why Julia is a bit slower than FastJet. I'm convinced that it could be as fast, but it's just not quite there. Anyway, I mean, in the end, I guess the conclusion is we have a very optimized C++ package, and we got as fast as that, and even a little bit faster in Julia without a terrible amount of effort, actually. So what's the current status? So based on the experience that we gained, we thought, okay, this is actually worthwhile. We should release this as a proper package in Julia. So the lesson here is that, yeah, it's one thing to write some decently performing code. It's quite another to release it as a piece of code that other people could actually use. So I spent quite some time doing cleaning up and writing documentation and making sure that people could actually use the package. I have to say that for writing documentation, Copilot was kind of amazing. You could just highlight the method and say, okay, document this. And it didn't get it right all the time. It's kind of interesting. We have this p-value, which is this power. It kept thinking that must be momentum, because surely in physics, p always means momentum. No, it's not quite. But it certainly saves you a lot of time. You have to look at what it does, but it saves a lot, and you get nice comprehensive documentation. And then I think when you start to work on these things, what's nice is that maybe Julia's gathering a bit of momentum inside the field. So quite unexpectedly, we have a contribution for jet substructure, which is rather important, and tagging from some colleagues in CMS. And just before this workshop, I had contact from some people in Atlas that want to use it as well, so they're very keen. They particularly want the jet substructure. It's of definite interest for the FCC, so the potential future CERN collider that could be 100 kilometers and bigger than the LHC. Our colleagues in FCC actually do use a lot of analysis level jet reconstruction on the events. So there are a couple of slightly different algorithms that we want to implement, because the ones that we've implemented right now are more for PP collisions. That shouldn't be too much trouble at all. Okay, so we're coming to my conclusions. So I think jet finding was a really good example to try inside of Julia. The performance was, in the end, slightly better than FastJet, which is a very optimized package. So yay, that's pretty good. The ergonomics in Julia were a lot better. So even when we were doing the tiled implementation, the fact that we were able to do everything with just, you know, references and objects and not pointers leads to a lot better memory safety, and it was easier to reason about the linked list. It's much easier to profile and apply optimizations inside of macros, so we enjoyed that a lot. Overall, the tooling was a bit better. I mean, it takes you a bit of time to learn the tooling and the right pieces that you want to use, but once you get there, you're like, oh yeah, this is really nice. It's much more flexible because of the dynamic nature of Julia. It's much more flexible for users of the package to use their own data types. So together with a few other colleagues, we have a sort of a beta version for Momentum base package, which Uwe wrote. And the intention is that we can then very easily support input particles in anything that supports the 4 Momentum base operations. So the package is now live in the registry, and it's starting to pick up users. The core code is done, but there's quite a lot to add to get to the state of the art, particularly the substructure and the taggers, but they shouldn't be too difficult. And yeah, it was a good experience. And let me just finish by saying, as Perry did already, we hope that anyone that's interested in high energy physics might take the opportunity to visit CERN at the end of September, where we will have our second JuliaHep conference, which we look forward to a lot. Okay, thank you for your attention.
Thank you, Graeme.
Yeah.
That was very interesting. It's always interesting to see, you know, a large algorithm, non-trivial algorithm implemented, and sort of showing that the micro benchmarks aren't that bad and aren't that wrong. Mm-hmm. So that's very interesting. We have time for a couple of questions, I think. Is there one? Two? Perfect.
Even three.
Mm-hmm. How would you compare the number of lines of the Julia implementation with the C++ implementation, or just the developmental time in general?
It's definitely less. I didn't do the count lines of code. FastJet has quite a lot of different bits and pieces in it, though, so just a naive counting of the lines of code wouldn't tell you properly how things were. But as I already illustrated, there are definitely places where Julia's syntax just makes things more compact, like the broadcast syntax, which is a little bit more involved in C++ if you want to do it. So I think it's less. My guess is that I don't know how long the FastJet developers took to develop, so it's hard to say, you know, the development time overall. But I would say that Julia has definitely a more comfortable development experience. Yeah, it's probably faster to do it there.
Do you know the compiler which was used for FastJet?
Yeah.
So, for example, Intel is still ahead of GCC, even nowadays, I think. Background.
Yeah, so this was with GCC 11.4. I've compiled FastJet a number of times during the course of this development, and I don't see any major changes with the compiler. It's -02 actually as well. FastJet, for its sins, uses auto tools, which if there's anything that makes you feel like CMake isn't so bad, try using auto tools. It's truly awful. So yeah, it's you could try optimizing FastJet even a bit more. You might be able to squeeze a bit more out of it.
Any last question? Okay, there's one there.
Thank you for the talk. Have you tried integrating this into the rest of the Atlas code base? And if so, how have you found integrating Julia with, say, C++ and Python?
Okay, no, at the moment we haven't. I think there are some things that we need from Julia to be able to do that. I think realistically, if you were to try and get this into the Atlas code base, you really want a statically compiled library that doesn't bring along the Julia runtime. You just absolutely need that, because you're having to fit it into what is already a massive C++ enterprise. So we have thought about how to do it, but at the moment I think we need to wait and work on things like static compilation to make that realistic. So I think that one of the things, we're kind of targeting the analysis side of things, where users are reading some final n-tupled products and then maybe wanting to do some reconstruction of the jets at that point in time. And that's definitely would work for the FCC, where FCC-EE is right now.
Thank you very much. I will bother you outside with other stuff.
Sure.
Only one comment I would like to make on the table you saw with the numbers where Julia was slightly slower than the fast jet. Actually, we had a similar item because we also compared C++ code with Julia code. And it is somehow strange that at some point it is initially C++ is faster, which seems like that the implementation of C++ is good. And then as the data goes bigger, the Julia goes extremely faster. And then the even higher, you have something going together, but Julia seems to go slightly slower. So we had the similar behavior in a completely different item. Yeah, thank you very much for the nice presentation.